Who knows where I left off? What was the last thing we were talking about?
Groups.
We said we're going to start with groups today.
Ah, okay. All right.
Hey, what's going on?
How are you?
So,
Grand.
group theory. Yeah, okay. All right. Now,
Real good stuff, guys.
Don't you mean a crummy start?
Huh.
It's bad. Crumbs or sugar or something.
okay.
So it's my cereal.
Ah.
I took it from the
We're off to a
plate. I'm
crummy
sorry
start.
about that.
Let's go.
Okay,
I had to finish it.
Oh, sorry. I remember the wrong page here. So, who can tell us what a group is?
So it has an identity, it has a multiplicative inverse, and it might not be abelian.
So what do you
Back
think?
up.
What is this here?
Let's call it Mark.
Volume, guys, volume. Keep it down.
Okay.
Or we'll have to close the door.
Okay.
Yes, that's precisely the point.
Yes.
What does it refer to?
So you have some type of a set.
Now you're talking.
What, you didn't like the Mubarak?
No, you just said it has
A
Right.
set with certain properties. It has an
Yeah,
identity.
here, I'll call the set G. To remind us that it's a group with certain properties. Now, properties, what kind of properties?
Now it has an identity.
What's that mean?
Group. So that means
What do you mean by
G, let's say there are at least two elements, or at least one element in your set, and it's not the empty set. And
Okay.
if we take this one element and multiply it by itself.
Wait,
it's a-
what do you mean multiply?
Oh no, you can't have
some-
one
you
element
have
to
have-
multiply.
It's a set, a group is a set with some operation.
So if you say set,
One operation.
So there's
One.
an operation.
yes.
Yeah,
Okay.
one operation.
Now we can start talking about properties.
Okay. Now this
We
is
have
the
a-
eat,
we have
right?
a set and an operation.
That is the eat he was talking about. The set and the operation.
Yeah.
He said
that-
it has.
equals it.
Yes. Okay. Okay.
That's the it.
Okay. Okay. There we go.
That is the it you were talking about.
Yeah.
So, precision. Right, so now, what properties?
So if you take an element in
Yeah.
the set,
Mhm.
let's call it little g, and you multiply it by another set, another element in the set, let's call it g2, then, one of them could be the identity. There exists some element such that g1 times this element equals g1. That's the better way to say it.
That's beautiful.
Yeah. E.g.
Davis, what else exists in it?
Here's the way I like to say it.
Uh-huh.
This properties. This is the existence of an identity.
Yeah, sure.
What about the closure?
Yeah, that's an important one too.
Well, and now that we talked about the identity,
No, there aren't important and unimportant properties. There are only essential properties. If you don't have them all, it's not a good
Trouble.
Okay, so what does this say? There exists an E in G such that EG equals GE equals G
Yep.
for all G and G.
Yes.
beautiful.
Okay? So, yeah, let's talk about closure. What's closure?
That means since you've written G1 and G2, G1, operated on G2 is still in G.
Yeah.
For all G1 and G2.
So no, using the operation never takes you out of the set.
Yeah.
Yeah, that's right. Okay, good.
Oh, there's a third one.
Those elements of the group should
Therefore,
have inverses.
Yeah,
Yes.
inverse.
You'll be
for all G in your set, there exists G inverse in your set such that G inverse. I'm omitting the formative writing. You just write it next to each other. Is the same as G inverse G is equal to E.
Mm-hmm.
You have a question? Are you familiar with this?
Oh, yeah, but
Okay.
somewhere I read that you can also have a left identity and a right identity.
With infinite groups, let's see. That's possible. Let's see. What's the statement here? There are weaker objects than groups where you can have distinct left and right
That's
identities.
not really a group then.
Right. Yeah.
Okay.
Because well, let's see. I wonder if we can even prove it from here.
Well, it's the. What are you talking about?
Yeah. If all right, suppose GG inverse is the identity.
Well, I mean, you have G has to equal GE up there by
And
definition.
G inverse, if I multiply, so if this is a left identity, let's see what happens here. And I multiply by the right identity, then I'm going to get E times G right, which has got to be G right. But G with the left identity has to be 1. So this has to be G left, so the two are equal.
So it's a theorem. You can prove that.
I just proved it. Yeah. So, but you can define a weaker object where you have distinct ones. All right, what's the last property?
So we have an identity associativity.
Yes.
Then do you want to go one step further and do the fifth one that's a special group?
What are you thinking of?
He's talking of S's. Special
I'm
group.
thinking of a special group, call it an able something. An
abelian group. Good. Yeah. Those are boring.
Is it boring?
I know. Why is E and M like the non-abelian ones the one we use?
Yeah, right.
Abelian group. So in the Poincare group, where we have Lorentz transformations and translations, all of the translations commute with one another. Translate this way and that way, you get the same places that way, this way. So, okay, we encounter abelian groups. Most often, we're going to be thinking about rotation groups, which, except for the one with only one generator, the one-dimensional U1 or O2, are non-abelian. So rotations do not commute. And it's easy to check that just by rotating a book or something. Okay, so these are the properties of a group. So you talked about a group. What if G has one element? Can we do that?
Yeah.
So if we let G be a single element, let's call it G. Well, G had better be the identity, and G had better be the identity, so it's own inverse. And associativity is pretty irrelevant, so we're good. We've got an identity, we've got inverses. It's associative. Any number of products of G's reduces to either E or, but E is G. So any number of products of G's ends up as G. All right, not a very interesting group. So let's go to two elements and see what we can do. Let's let G be the set with two elements, and let's set up a multiplication table. And one of these has to be the identity. So let's call this one the identity. And we can fill in the multiplication table because that has to give whatever it multiplies by. All right, now, what goes in the other corner?
Well,
right, there has to be
B below B.
Yeah, so we're asking what B times B is. And let's see.
It has to be either B or E, right?
Yeah, the problem here is, let's see, can it be B? That's the question. I'm on the verge of just putting E there, so B is its own inverse. But what would happen if B times B was B? Then then if I multiply by, if E times B is B rather than E, then if I multiply by B inverse, which has to exist, that gives me E. Wait a minute, what did I do? But this is E, so that says B equals E. So I'm back to one element. So it's a contradiction to say B times B is itself, it has to be E. Then B is its own inverse, and you can somewhat tediously check associativity, but since every other element is E, it's not going to be very complicated. Let's see, let me see, so you can go on to 3 and 4 elements. Now, it turns out this is the only 2-element group, and we didn't even say what the operation was. So we can think of different ways of writing this same group. So suppose that this is addition mod 2. Right? You guys are familiar with modular addition? Right? Everybody?
Not me.
Yeah.
So,
I mean, I
I-
should be, but I'm.
10 plus 3 equals 1.
Yeah.
Remainder.
Okay, so it's like adding on a circle,
Okay.
right? So if I add 2 and 2, I get to 4, so I'm over here. If I add 4 and 5, I get to 9, but 7, 8, 9 comes back to 2.
I see.
It's once you get up to 7, you're back to 0.
Got it.
Right. Modular addition. So mod 2, then we can take 0 and 1 here. 0 plus anything is the thing, and 1 plus 1 mod 2 is back to 0. Or, what if I take multiplication, ordinary multiplication with 1 and minus 1? It's the same group. So the numbers 1 and minus 1 under ordinary addition, or the numbers 0 and 1 under mod 2 addition, actually are the same group. So the underlying mathematical structure is the same for those. You use them in different ways, depending on what else you were interested in. I think as an exercise, I suggest that you find all groups with 3 elements, find all groups with 4 elements. It turns out I think there's only one possibility with 3 elements. I think there are 2 possibilities with 4 elements. There are 2 different groups you can write with 4 elements. These are finite groups. They're the kind of groups you use in, say, crystallography, where you have some discrete number of rotations that brings it back to the same configuration. You use it in field theory too. There are discrete groups like parity or time reversal or charge conjugation that basically have 2 elements, right? 2 eigenvalues, 1 and minus 1. These occur and are very useful. There's an extensive theory about finite groups. You can prove all sorts of results in general about their structure, elements, and properties. What we're going to be interested in, more particularly though, are Lie groups. Lie groups are groups where the set, we've got some kind of operation. I'll just write the elements next to each other for the operation, whatever it is. But a Lie group, the basic property is that every group element of G can be labeled by finitely many continuous parameters. So let's call them real parameters. So every G can be written as a function of some X element of Ra. N real parameters, where these parameters may have some definite range. They don't have to span all of Rn, but yeah, let's say some open n-dimensional set, which is a subset of Rn. That's a little closer. Yeah, this it doesn't. It's probably not an open. It's actually probably a closed set, or half open, half closed. Anyway, there's a range. Let's do some examples. You know what this means, actually, is that let's think about what kind of object we're talking about here. Now, because of these four group properties, groups tend to be geometrically very nice. But if this is my group G, and this over here is Rn, where those lines are all perpendicular, then writing G as a function of some vector x over here and some parameter set is a map from this space into the reals. And that's an invertible map. You give me a point in this neighborhood and it gives me some unique G over here. What does this sound like? What kind of object has this kind of map, an invertible map with Rn?
Manifold.
A manifold. Yeah. A Lie group, let's say the physicist's definition of a Lie group, it's a group that's also a manifold.
Perfect.
So we know what that is. There's an overlap condition like there is with a manifold, and they're.
So other than the real group, are there no other groups that have this property, being a manifold?
Well, none of the discrete groups, right? Because they only have a finite number of elements, can't be a manifold.
Okay.
Right. It's only Lie groups where we can parameterize all of the elements by n real numbers, and then it's called an n-dimensional Lie group, and these let's see, we should come up with some examples.
Can you parameterize, give them complex parameters?
You can complexify Lie groups, and that can be confusing.
Yeah.
Right. But yes, absolutely, you can complexify, and people do complexify. A Lie group over the complex numbers is fine. Of course, that can always be written as a Lie group over the reals.
But you can never write it as an octonian type thing. Because they
Debian and Corinne do this all the time, right?
Yeah.
They write matrices with octonian valued elements in the matrices, and up to 3 dimensions you can make those things Hermitian. Well, this is a way to describe the exceptional groups. Right? They're basically the generators of unitary transformations, except that the elements are octonionic, and so it becomes a very complicated and large thing. Tevian Gray and Corinne Montague, they have a book out on this with World Press, I think it is. They've been here a few times to talk about the octonians, quaternions. This is a good way to understand certain very special groups, including the exceptional Lie algebras. The Lie algebras a Lie group. I'm getting ahead of the story. A Lie group can be a product of groups. You can form products of groups. So you could talk about some ordered pairs where G is an element of one group and H is an element of some other group, and define a suitable multiplication just as a direct product. So you can form as many groups as you like, and you can ask, when a Lie group is a product like this, or is, in some sense, simple. Well, there's a well-defined notion of a simple group, and the simple groups have been classified. Let's see, the simple groups, let's see, how would I define a simple group? There are simple groups, there are semi-simple groups, and then, there are various more complicated things that you can decompose into those. The semi-simple groups allow the construction of a non-degenerate metric of a sort. Mm-hmm. But that requires us to talk about the Lie algebras. So let's get some examples of Lie groups first.
So just to clarify, they don't have to be continuous real parameters. They can be like continuous complex or...
No, for our purposes, they have to be continuous real parameters.
Okay, but in general...
We want our structure constants real.
Yeah.
Right. I made this mistake one time where I was trying to construct a supersymmetry group and ended up writing the complexification instead of getting truly fermionic generators.
Yeah.
You got to be careful with your signs.
Yeah.
But when we talk about Lie groups, we're talking about real parameters. Although the complexifications do exist.
Okay.
All right. So let's think of Rn as a vector space, an n-dimensional vector space. Right. We can do that, and then any two vectors in an n-dimensional vector space, right? That closes. Certainly the sum of any two vectors. There's a zero vector element of the n, which is just all zeros. And if I add that to any vector, I get the vector back, and that works either way.
So here are x and y your basis, then?
No, they're just two vectors. Any elements of the vector space.
All right.
So yeah, this. Whoops. Not theta, 0. And then for an inverse, x vector inverse is just minus x. Because you add x to minus x, you get the identity. And addition of vectors is associative, and so this is a Lie group. And because notice each vector can be parameterized by n real numbers. So, very simple case. The operation is addition. So the set of vectors together with vector addition form a group. And that's an n-dimensional Lie group. Let's take something more interesting. Let's take matrices. Let's take n by n matrices. Okay, so we know how to multiply them. Let's call this set curly m or something. The set of all matrices where our product is matrix multiplication. Okay, so the product of two matrices is an element of M. Then we have an identity matrix. That's an element of M. What's M inverse?
It might not exist.
That might not exist. So,
yeah, you need to have a non-zero determinant.
yes. So we're going to look at the equally large set of invertible n by n matrices. These still have n squared parameters. You've thrown out a set of measure 0.
Yeah.
Right. So all matrices of non-zero determinant. And then we know that M inverse exists by fiat. We've chosen just those. Let's check closure. You know, if M and N are both in M, okay, their product, well, is their product invertible? It is, because the determinant of Mn is equal to det M times det N. And since, by assumption, these are in the group and therefore non-degenerate, neither of these is 0, so the product is not equal to 0, so Mn is in the set too. So it is closed. And that's everything we need except associativity, but matrix multiplication is associative. That's easy to check if we use index notation. If I have Mij, Njk, P, K, L, it doesn't matter whether I multiply these two first or I multiply those two first. I get the same thing. You know? So matrix multiplication is associative, and they form a group. This group's important. It has a name. This is, let's see. So I can write it here. So the group is the linear group because it's matrices acting on some vector space, right? N real dimensions is the collection of, that's a really ugly letter, with the matrix multiplication as the operation. This is the general linear group in n real dimensions. Now we can make these complex matrices too, right? Clear how to complexify this one, and the results still hold. In fact, as you know, we talk about the unitary groups. The thing that you want to be mindful of is when we get to the Lie algebra. We look basically at the tangent space to the group manifold, and there we find a vector space called the Lie algebra. And the Lie algebra has an antisymmetric commutator product, where the commutator of any two generators, we call them, is proportional to another generator, where the proportionality is real. Right? Otherwise, you're doing something different.
So the structure constants have to be.
The structure constants have to be real.
For any Lie group or just the ones that?
For any Lie group.
Does they have any consequence in quantum mechanics?
Well, it's used a lot in quantum mechanics.
Does it have anything to do with the what do you call them, observables being real?
With the observables being real? Yes. The group that's relevant for quantum mechanics is, well, just for, say, a simple scalar wave function, complex wave function, is the unitary group U1. And the operators we work with in quantum mechanics are Hermitian matrices. Now, you can prove that you can use a U1 transformation to diagonalize any Hermitian matrix. And the property of its being Hermitian is that when you diagonalize it, those diagonal eigenvalues are real. That gives us a way to extract real number predictions from the complex wave function or complex valued operators. All right, so now GLN is not actually a simple group. It's a product of two commuting subgroups. So what we want to do is extract the two parts. Let's let M be an element, or let's let M tilde be an element of GLN. And if I don't specify the field here, then I assume these are real matrices. All right, we can have GLNC or GLNH for quaternions or GLNQ for octonions.
Yeah.
Right. So we can build matrices of different kinds out of different fields.
Mm-hmm.
The structure constants are still going to be real.
Yeah. Gotcha.
Okay. Now let M tilde be written as the determinant of M tilde times some M. Let's see, is this the right power? So if I take the determinant of this, I'm going to, so the determinant of M tilde is the determinant of M tilde times the determinant of M. Therefore, this has got to be equal to 1. So, to see how we use this, we need to talk about the idea of a representation. A representation of a Lie group, or any group, but we're interested in Lie groups, is a space that, really any mathematical object, but generally a space that the group acts on. So I can choose some space, I can specify how my group shuffles the different elements of that space. Now, let me give, let's see. Yeah, one example where the shuffling is not simple is if we look at the conformal group. And this gives us another example of a group. All right, so let's say on R3. So conformal transformations on R3, one thing we can do is a translation. All right, so that's a nice linear transformation. That's very simple. Okay, we can also do a rotation. Let's see, meant to do this the other way. X tilde I is some rotation matrix. Well, rotation matrices times their transpose give the identity. That's the property that preserves the length of this vector. Mm-hmm. And we'll be looking at those in more detail. But also, you can have rescalings where x tilde is some multiple of x. And that's nice and linear. But there's another transformation. Here's a discrete transformation. If I let x tilde be x tilde, or x divided by the squared norm of x, it's called an inversion. And an inversion preserves ratios of lengths, the defining property of the conformal group. There are many. Preserves angles or preserves ratios of lengths. You can write sines and cosines as ratios of lengths, so those are the same thing. Mm-hmm. But preserving ratios of lengths, if you look at the length of this x tilde, then you're going to get 1 over x squared, and then x dot x. But that's just a factor times x dot x. So it's a conformal transformation. It preserves the norm of x up to an overall multiple. If I do a combination of this, that's a discrete transformation. I do it again, I come right back. So this is a 2-element group. But if I combine this with translation, so I do an inversion and then a translation and then another inversion on x. That's inversion and translation on this thing, x over x squared. And I translate that, I get x over x squared plus some constant vector. And now I invert that, I get x over x squared plus b over the norm of this thing is 1 over x squared plus twice b dot x over x squared plus b squared. And if I multiply it through by x squared, it looks somewhat simpler. I get x plus x squared times b. That's the magnitude there. Then here I get 1 plus 2b dot x plus b squared x squared. That's not a linear transformation, right? Nonetheless, it maps R3 into R3, assuming we do need to add a point at infinity, so the inverse of the origin is there. So it's just defined as the inverse of the origin. But this is an example of a representation of a group on R3 that is it's not a linear transformation. It does some horribly nonlinear thing here. Mm-hmm. All right. Now we can deal with those. It turns out for the conformal group that we can actually find another representation of the same group. And we saw this with just the two-element group. Different representations as 1 and minus 1 under multiplication, or as 0 and 1 under addition mod 2.
Or the B and the E, right?
Or B and D, yeah. That's in some sense a more general representation, right?
Yeah.
The A and the B.
Yeah.
Yeah. So we have different representations. Right, for our purposes, a representation of a, let me say it more carefully, a linear representation of a group is a vector space on which the group acts. So suppose I have a group that acts on a vector space. So I can take my group element on some vector, and that's an element of my n-dimensional vector space, you know, for all G. All right, well, then automatically that's got to be a linear mapping because vector spaces are linear, right? It has to be the case that G on a linear combination of vectors, you know, is a linear combination of G on V plus G on W. Otherwise, it's not going to preserve the vector property of the space. And things that do that are matrices. So in saying that a linear representation of a group is a vector space the group acts on, automatically tells me that I can write the group elements as matrices. And so the groups that we're going to be most interested in are going to be subgroups of GLN. Okay, so now back to the problem. Sorry, back to the thing I was looking at over here, where I can write any element of GLN as the determinant, its determinant times an element times another matrix M, where the determinant of n is 1.
Is this G that you wrote out, is this like linear, bilinear over here? Or that it just went on like that?
Let's see. It has to preserve the linearity of vectors. So if I transform all the vectors into space,
yeah.
Well, the transformation of a linear combination of vectors has to be the same linear combination of the transformed vectors.
Okay.
Right. That's what I'm saying here. Did I answer the question?
Yeah.
Okay. All right. Now, if we look at a linear representation, so all right, we're talking about matrices here already. So M acts on some vectors to give some other vectors. And if I decompose this as the determinant of M tilde times M acting on V, then I'm just going to get the determinant of m tilde times, let's see, what do I get? Well, how do I want to say this? Let's see, the effect of m tilde.
So did you flip m tilde and m? Is m a new thing inside there?
Yeah, I define m here. Right. This defines.
Oh,
yeah.
Okay.
So I write a matrix such that m tilde is its determinant times m. So the determinant of m is 1.
But determinant of m tilde is. Oh,
Is in terms of m.
That doesn't help. Yeah.
Mm-hmm.
Yeah, let's see. Yeah, what is this? I can. So what am I going to get? I'm going to get 1 over det m tilde times u. So I just get a rescaled u if I act with m. I'm not getting it quite what I want to say here, and I'm not sure that I've quite written this down. Let's see. Yeah. We need this to be the 1 over n power, right? Because, yeah, if I multiply every element of m by some constant and take the determinant, I'm going to get the determinant of the m. I'm going to get the effect of the m power.
Yes.
So that then, let's see, taking the determinant of this is, yeah, so then this line was right. Det m tilde times det m. So we get a unit determinant matrix. I don't want to say this. These are subgroups. The point is that if I take any 2 unit determinant matrices, equal 1, then the determinant of their product is also 1, because the determinant of a product is the product of the determinants. Each of these is 1, so the determinant of the product is 1. So unit determinant matrices close. So if I have 2 properties, m is an element of GLN, and det m equals 1. This defines a group. Okay, I just showed it's closed. Every element of GLN has an inverse, so I can write the inverse, and that's equal to the identity matrix. If I take the determinant of both sides, I show that the determinant of the inverse has to be 1. The associativity follows because they are matrices, and so these form a group. This group is called the special linear group in n dimensions. Special means the determinant is 1. This property comes up all the time because the determinant is just a factor that commutes with what the rest of the matrix does. So you can write GLN as a direct product of the real numbers that you get for determinants and SLN. So we found another group, and this group, the special linear group, is a simple group. Now,
So the ones that have the determinant not 1, just minus 1, apart from being not special, do they have any other name?
Yes. Yeah. When we talk about orthogonal groups, this comes up. yeah, not so much with linear groups, but and I'm about to introduce orthogonal groups, but among orthogonal groups, right? Orthogonal groups preserve the norm of vectors, right? So this is going to be the same as the transformed version of X under an orthogonal transformation. Well, if O does that, then minus OX with minus OX also does this. The minus sign is just going to go away. So for every orthogonal transformation, minus O is also an orthogonal transformation. Now, those may or may not be closely related. Right? The issue is, in fact, whether the manifold, right, the group manifold, we call it, is connected or not. And so I can ask, okay, for two-dimensional rotations, I've got some matrix A, B, C, D, and we'll show that the transpose needs to equal the matrix. Now, you might think that, all right, one that takes x to minus x would be minus the identity. So, all right, certainly minus the identity acting on x gives minus x and preserves the norm. So now we can ask whether there is a sequence of rotations that relates this to the identity. Right? So if this is the group manifold, right? So this is our orthogonal group, say. Right? We've got the identity element here. Somewhere off here we've got minus 1. Or it's possible that we have two connected pieces and minus 1 lies over here and 1 lies over there. These are only connected by a discrete transformation. Well, it turns out that in two dimensions, if basically think of this as x and y, right? If I map with minus 1, essentially now I'm mapping x that way and y that way. Y goes to minus y, x goes to minus x. But notice, if I just rotate back, a rotation by pi brings it back to what it was. So there is a continuous sequence of rotations by angles between 0 and 90, or I'm sorry, 0 and 180, that will rotate minus 1 into 1.
And that part of it being continuous is part of the thing that makes it a Lie group.
Yeah, the fact that it's continuous, yes.
Yeah.
Now, it can be continuous within two separate pieces.
Yeah.
Right. So what we've shown is a 90 or 180 degree rotation of the identity is minus the identity. And that's a continuous transformation because I can do any angle between those.
Mm-hmm.
Okay, if we go to 3 dimensions, on the other hand, and I look at the reverse here, well, I can do the same trick and I can rotate 2 of these back to where they were, but I always have an odd one. So in odd dimensions, there's a parity transformation. The parity maps every vector to minus that vector. And there's no way that I can, if I've acted on a vector with this, so I've got some x, y, z, I'm going to get x, y, and minus z. Or minus x, minus y, minus z if I haven't rotated anything. There's no way to continuously rotate this back to x, y, z. And so for O3, we find that there are 2 different continuous sets. There are transformations. Notice the determinant of this is minus 1, whereas the determinant of the determinant of anything that doesn't change the sign, determinant, determinant minus m is -1, determinant of m is +1. There's no continuous way to move one of these into the other. So you get basically two copies of the connected component of the identity, right? So if you look at all vectors you can get to by doing as many infinitesimal transformations from the identity as you like, it'll fill out a manifold. But there's a whole other identical manifold that have the opposite determinant. Yeah, when we do this for the Lorentz group, there are actually two different discrete transformations. You can reverse time because you've got this minus sign in the metric. You can do time reversal, or you can do parity on the 3 space. So in Minkowski space, you actually have 4 different connected components. You have the time reversed components, and you have the parity reversed components. So you have 4 different components to the Lorentz group. When we deal with Lorentz transformations, it's easiest to deal with the discrete transformations independently of the continuous ones. So to deal with the continuous ones, we talk about the proper orthogonal Lorentz group.
Spell that? Wow. Right? You're going to make a mistake. OUS at the end.
Yeah.
Yeah. Look it up.
Close enough. We're not English major here.
Yeah. All right, so here we have vowels.
Is that the name of someone?
No, chronos is the Greek word for time. Orthogonal.
Yeah,
right.
So are we running out of names?
Orthogonal means preserving the direction of time.
Oh,
yeah.
All right. So we look at the time, future preserving Lorentz transformations. Proper is like the difference between a proper vector and a pseudo vector. A pseudo vector behaves the wrong way under parity. So proper means that we preserve parity. Orthogonal means we preserve the direction of time. And now there's only one connected component to the proper orthogonal Lorentz group. Okay. So now.
octopus.
Right.
Was that the octopus group?
Octopus.
Yeah. Okay, so let's see.
Yeah, must all the groups have a +1 or -1 determinant?
Well, yeah, we will generally work with the special linear groups or the special orthogonal group where we hold the determinant to 1. So to get here, we can look at determinant 1 transformations.
Dr. Willis?
Yeah.
Oh,
yeah.
From what I remember, determinants, don't they, when you have a linear transformation?
Yeah.
The determinant shows you how the volume expands. If the determinant is 1, does that mean it preserves volumes?
Yeah, I think that's right.
Right. So
so
the special linear group preserves volumes when you map, right, from one space from the space to itself, right?
It's volume presumed. Gosh, now we have to try and prove that.
Right. And then the determinant
right.
-1 means that the volume is still preserved, but it's somehow got a different
you're talking about oriented volumes.
Right.
So is it a right-handed rule volume? So you have like your triple product in 3 dimensions.
You put a
B cross C. And you can cycle those. That's a volume. Right. And I can write this as epsilon I j k a I b j c k. And the presence of that epsilon tells you immediately that it changes under parity. Right? When you do analytic representations of all these things as matrices, the Levi-Civita tensor is always your key that something violates parity. Two of them can always be written in terms of the metric in Kroneker's. Now, if we ask what happens under rotations, if we have a determinant one rotation, right, that preserves volumes, or that preserves parity, then we're going to transform A and B and C, and where can I do this here? So we have the new volume is epsilon I J K M I L M J M M K N A L B M C N.
It's obvious.
Right. But the Levi-Civita tensor, along with the metric, is semi-unique. Those are the only two matrices invariant under rotations. Right. So this is epsilon LMN.
What about the second fundamental form?
And we've proved, and so this is equal to the original volume. So proper rotations preserve volumes.
That has determinant one.
Yes.
Yeah.
All right. You'll what this will give, if m is not determinant one, you're going to get the determinant of m times epsilon here. Right. So you need determinant one. So elements of SO3, proper SO3. So all right, SO3 has determinant one. So they're proper transformations. Those preserve volumes.
Is the second fundamental form also special? Like you said, the metric and the Levi-Civita tensor.
Well, the second fundamental form is a tensor.
Yeah.
So it transforms linearly and homogeneously under whatever transformations preserve the manifold.
So
probably general linear transformations, or if we're doing it as a like in orthonormal frames.
Yeah.
We'd have local Lorentz or local orthogonal.
So it'll be preserved under rotations also.
Yeah.
Okay.
Yeah. Oh yeah. Okay. So in general, there are a couple of ways that we can restrict the general linear and special linear groups. Suppose we ask, all right, for all m in GLN, let well, no, that's not fine. Let's see. Consider the set of elements of GLN such that let's see. I'm writing this a different way. Let's call this A. Let's let A and B be elements here, and I want to fix some matrix A, M. Fix M such that A, M, and I want A transpose. Transpose to give me, and this should be thought of as doubly covariant. All right. I want to argue that defines a group. So, right, the reason I write it this way, if M was a mixed type matrix, then I would write A Ki here and A inverse on the down index, Jm to get, and I would ask for that to be Km. When I think of M as doubly covariant, then I'm going to just put an A on each one, Jn. And now if I bring this one to the other side, I can write A I M as A transpose mi. So I can write this as A transpose mi, A I j, A j n. And in matrix notation now, this is A transpose times A times, M, A transpose times M times A. So I probably should have said this, let's say that the other way. Is that right? So I need the transpose of this one to land on that side. So a similarity transformation leaves M invariant, and I can write it in matrix notation as A transpose MA gives M back. So now consider a product of two matrices, and suppose...
Does A have to be in this special linear group for that to happen? Because it doesn't seem like...
No.
Because it's not A.
No, it doesn't have to be special.
Yeah.
All right, so now what I do need is determinant of A transpose times determinant of A to be
1. Right?
To be 1, yeah.
That's what I was
All right,
doing.
but it could be -1.
Yeah.
All right. So if these are real transformations, which is what we're doing, then det A does equal det transpose A.
Okay.
So the determinant has to be plus or minus 1, and that shows there are two connected pieces, right?
Yeah.
It can't be.
Okay.
All right, but what I want to show here is if I let A and B, let's define this to be O, be elements of, well, no, it's not quite O yet. What do we want to call it? Let's just call it S. I want to show that S is a group with matrix multiplication. So if I take two elements of S, and I take A times B, transpose acting on M times AB, then the transpose of AB is B transpose A transpose. And I've got it. Because it's associative, this is equal to M, and then B is in S, so,
Which is similarity.
so this gives, yeah. So that implies that AB is an element of S. Okay, in order to be in S, these have to be invertible. Well, the inverse of AB is just B inverse A inverse, which is an element of S. So the inverse is there, and it's associative because they're matrices. So the set of elements of GLN that leave some matrix invariant form a Lie group.
You have to show that identity exists also.
Oh, the identity. Yeah, thanks. All right. The identity leaves M invariant.
Yeah.
Okay. Yes, but you're right. 1 M 1. 1 transpose M 1 M.
I like that one.
There we go.
That was
Yeah.
simple.
Yeah. But yes, right. We have to have that. Yeah, we've got the inverses. We've got the closure. So now there are two interesting subcases because S decomposes. Right? I can let M be.
How's the reason that you know it decomposes?
I'm showing you.
Oh.
I can write it as the sum of a symmetric and an antisymmetric matrix. Right? And because I can do that, let's call that M is M symmetric plus M antisymmetric. Now, if I ask what happens if I do a transformation, let me find where I've talked about this just to, right, so what we have is A transpose M A is M, but I can write this as A transpose M, M symmetric plus A transpose M antisymmetric. But if I take the transpose of this whole relation, let's see, the transpose of A transpose MA is equal to A transpose M transpose A transpose transpose. It reverses the order and transposes everything, which is A transpose acting on, it's going to be M symmetric because it's symmetric, but minus MA, and then the double transpose is A again. So this is the transpose on the symmetric part minus the transpose MA on the antisymmetric part.
Could you repeat that second step there? I missed.
I'm writing M transpose. Write M as a symmetric plus an antisymmetric.
Yeah, sure.
The transpose of that is MS minus MA because they're symmetric and antisymmetric.
Cool.
Right. So I've just put the transpose in.
Oh yeah, cool.
All right. So now, let's see. This is. Let's see. How do I want to say this? So preserving a matrix M that has both symmetric and antisymmetric parts is let's see. Let's see, this hasn't given me exactly what I expected. Hang on. So, yeah, so this ends up being a preserving M transpose. Yeah, I was hoping to add and subtract these, but I'm transforming a different matrix. The argument still holds, though. The point is that the let's see. What is the point? Sorry, I'm tired today. Yeah. If we consider the set of transformations that preserves just the symmetric part, then the transformations that preserve all of them are going to be fewer because they have to preserve the antisymmetric part too. All right, that's what I'm trying to get at. That preserving both parts of some fixed matrix is a stronger constraint than preserving the symmetric or the antisymmetric parts singly, right? So what that means is that if I want to find larger subgroups, what I should do is preserve a smaller set of matrices. So what we find is that if I take some symmetric matrix, and we'd like this to be non-degenerate, so the transformations actually do something, and I ask for transformations that preserve that symmetric matrix, this gives me a subgroup, and it's a larger subgroup than would be in the group that preserves some general matrix. I can also ask for some other transformations that preserve an antisymmetric non-degenerate matrix. And that gives an interesting subgroup as well. Now, these groups, if M is non-degenerate, actually we can do some rotations and rescalings of the vector space and show that we can diagonalize M. In fact, we can make all of its diagonals plus or minus 1 if we like. Well, you know what happens if M is symmetric. All right, that M is a metric. Mm-hmm. And if we choose an orthonormal basis for our vector space that diagonalizes that matrix, then M can be written as some number of 1s and some number of minus 1s, where let's say we have P of these and Q of those. The group that preserves that is called OPQ, the pseudo-orthogonal group of signature. Signature is sometimes written as P minus Q, but more often you'll just see signature PQ. It's just a little more immediate. That signature is preserved because this whole matrix is preserved. And the group that preserves those will be the orthogonal group. We're preserving an orthonormal metric, or a pseudo-orthonormal metric. So, for instance, O31, right? The Lorentz group with 3 space-like and 1 time-like, or what we've been doing, O13. Essentially the same group. Preserves 1, minus 1, minus 1, minus 1. This would be O13. Then we can ask for the unit determinant ones. So then we get SOPQ as the unit determinant pseudo-rotation group.
Say that again?
If we require the determinant of this rotation group to be 1, it's called the special orthogonal group signature PQ.
Okay.
Thanks. So these are the groups we're going to be really interested in a lot.
So for all SO groups, it is required that the determinant has to be 1.
Yeah, that's what the S means. Special means unit determinant. That's right. Now, what are these other ones? All right. What happens if we preserve an antisymmetric matrix? Well, we do require that matrix to be non-degenerate. So, in odd dimensions, all right, if you diagonalize an antisymmetric matrix, what you get are complex numbers, or pure imaginary numbers, right? Because let's see, it's it has to be minus its transpose. Mm-hmm. Well, if you generalize to complex, allow complex forms and diagonalize it with a unitary transformation, the diagonal elements have to be pure imaginary. Mm-hmm. All right, and they come in complex conjugate pairs. Oh, I'm too much at once.
No, please go ahead. Just think.
All right, let's see. Yeah, I can. We can diagonalize non-degenerate matrices, right? If they're real, then let's see. A real symmetric matrix can be diagonalized by an orthogonal transformation. Is that a familiar result? Just like Hermitian can be diagonalized by unitary. Yeah.
Okay.
All right. Now, are those results familiar?
So
a Hermitian matrix, the unitary transformations of quantum mechanics, can diagonalize them. The eigenvalues are real. For homework for Monday, prove that that the let's see, prove that a non-degenerate antisymmetric matrix must be even dimensional. There we go. that's all I'm really after, but there's a slick proof of that, and I'm not getting it just now.
Yeah.
But anyway, this group only exists in dimensions 2n, and it turns out you can put the antisymmetric matrix into a form where you have an identity matrix up here, an n-dimensional identity matrix up here, and minus the matrix down there. It's called a symplectic form. So these are the symplectic groups, SP2n, and let's just leave the S capital there, so we're talking about unit determinant. These are the transformations that, preserve this matrix, and these are the same kinds of transformations that make up canonical transformations in phase space, in Hamiltonian mechanics, right? You can write, if we call this matrix omega ij, then you can write Hamilton's equations as dx dt, xi dt is omega I, let's see, I want the inverse here, ij d times the gradient of the Hamiltonian.
Okay.
Yeah, if I let psi I be, let's make it A. Okay, there we go. Got it. Xi pi. Right. So 2n coordinates. Then this will be AB, and its inverse is minus that. But d psi A can be written as omega AB times the gradient of the Hamiltonian with respect to all the x's and p's psi b. So this includes both of Hamilton's equations. You remember one of Hamilton's equations has a minus sign and one a plus sign. And so if you split this into, if this is x, then you're going to get the plus sign here, and that'll be, let's see, dhdp is just, wait a minute, yeah, that's just the momentum. Then if you're differentiating p with respect to t, this is going to be the minus the gradient. You'll get a minus sign in the gradient of the potential. Is what happens. So the minus sign that you see between the two Hamilton equations is contained in this symplectic matrix. Now, canonical transformations are general coordinate transformations of phase space that preserve the symplectic form. A phase space that preserves Hamilton's equations, your symmetry is local symplectic. Right? So you do a coordinate transformation, but require that it be symplectic at each point.
The cows are actually outside.
Yeah, without horns.
Hornless cows.
This space is always even, right?
This is what
Phase space.
Yes, exactly. It has to be.
I didn't say anything. You said it. You said the cows are. You shouldn't be named.
Yeah, I
You are a cow.
The anti-symmetry.
Minus sign, you get
That's what gives them, yeah. So dp dt is minus dh.
Right, so that's why you have the
and the xdt is plus dhdp.
This is a formulation that is very elevated. This is not the way it's like.
Oh, no, yeah, we're not in the classical mechanics.
No. Do you have, what reference do you use for these topics? Do you have a book you love, or?
Oh, I don't know if I forgot the definition. I just look up Wikipedia and remind myself.
Anyway, maybe next time if you have some
Let's see.
good reference.
You know, there is a modern classical mechanics book, Abraham and Marsden.